To review our work of trigonometry, I'm not going to focus as much on right triangle trigonometry, which is your traditional sine, cosine, and tangent ratios. I'm going to first start with law of sines. So the nice thing about law of sines is you can use it with any right triangle, but in fact you can use it with any triangle at all. So usually we call those oblique triangles. So it's a ratio, so I'll remind you of what you can do. So it only uses sine. And what you look for is sine of an angle, and you compare that with the side opposite of that angle. And to set up the proportion, you need two fractions, and you should only have one unknown. So looking at this diagram, I'm going to mark the things you're going to start with. So you know that this angle is 65 degrees. You know this length is 100. The angle of elevation from the ground to the top of the tower is 32 degrees. We want to know the height of the tower, so I called that y. So if I was just to start in this triangle here, first of all, I notice this is not a right triangle, so heads up there, so I can't use right triangle trigonometry. I do notice it is within this right triangle, but unfortunately, I don't know any sides. I know a portion of this side. And then I notice this other right triangle here. So I could use right triangle trigonometry there if I wanted. So I would say let's fill in some angles. These are on a straight line, so this is going to be 115. And within a triangle, they add to 180. So I'm left with 33 degrees here. I finished this triangle off with 25 degrees. I'm going to work from this triangle here to the right to find this tower. So I want to find a length that's in both triangles. I could go after this length, or I could go after this length and look at the big triangle here as a comparison. So different strategies. I went after this length because then I can get into this little triangle on the right. So I said sine of 32. I'm going to compare that to the side across from it. So that's my x equals sine of 33, and across from that is 100. Little cross multiplication, or however you want to solve this to get x up top in the numerator. You get 97.29733. Notice I didn't round. Usually I would just leave that on my calculator too. From there, I could use law of sines again. Or, let me just change my cursor. Or, I could just use right triangle trigonometry. Say sine of 65, opposite that is the tower height I want, y, divided by the hypotenuse in this triangle, which is what I just found, at 97. Quick little multiplication across, you get 88 feet. So you can use law of sines to find angle measure. At this point in your math career, you don't need that as much, but just so you know, it's a possibility. So looking at this triangle, a couple things going on. We have similar right triangles. Sorry, this problem. Similar right triangles. We want to find an angle. So let's break down the language here. It says you have a right triangle, you have an altitude. Let me scroll this up. You have an altitude BD, so that's a right, that creates a right angle here. And it's drawn to this hypotenuse of triangle ABC. The entire hypotenuse is 16, part of it's 7, therefore this is 9. We want the measure of angle A. So first of all, we didn't have enough information to go right to trigonometry. I only have pieces of sides and triangles. I need at least two sides to use trigonometry to find an angle measure. So I looked at it, and I can go back and mark some angles here, as this is my large triangle. This is angle A. I'm assuming it's not isosceles. And actually, it wouldn't be isosceles because this altitude would then bisect this side. It definitely doesn't. So these angles can't be the same. So within the big triangle, I have a right angle and two other angles. Then I have these other right angles here. So I have lots of similarity going on. I'm going to focus primarily on the two inner triangles and show you how those are similar. So if I have two markings, a right angle, and one marking, two markings, a right angle, therefore this must be my one marking. Right angle, one marking, therefore this must be two markings. And again, we can redraw the triangles, or you can redraw one of them. I chose to say I'm going to focus on, I'll put it in a different color, this triangle here. Okay, and the reason why I'm working on this triangle, I want to include it because I want to find angle A. So let's try to get some sides. So this triangle here, and if I notice that if I look at this other triangle and I change the orientation, that's all I did down here, I rotated it 90 degrees, that I have enough information because they share this side just in different ways. So I could say 7 compares to x, the same way that x compares to 9, or however you want to move from one triangle to another, or if you want to stay within 7 over x equals x over 9 to set up your proportion. Anyway, all that just to find this side that's square root of 63. Now I have enough information to use a little bit of right triangle trigonometry. In this case, I'm using tangent because I know the opposite side and the adjacent side. I'm using my inverse tangent or inverse trigonometry feature, and I get 41.4. So on the back of this, we're really focusing more on a conceptual relationship between sine and cosine. But lots of things down here I'll try to walk you through. Notice I didn't put any numbers, so we're trying to make sense of this just in general. So in general, if I'm looking at A, sine of A would be the opposite over the hypotenuse. Cosine of A would be adjacent over the hypotenuse. Notice they both have a hypotenuse. And then following that same idea, if I'm looking at B, sine is opposite, so B over hypotenuse C, and cosine's adjacent A over C. So with sine and cosine, the hypotenuse is always the same, so that's fine. Let's look at these values though. So this one was A in my numerator, and this one's A in my numerator. So sine of A and cosine of B, they're equivalent because they're the same ratio. And similarly, sine of B and cosine of A are equivalent. So this happens only when these angles add up to 90. Notice they're not necessarily the same measure. They both could be 45. We don't know that for sure. But we do know that these trig ratios will be equivalent when the angles add to 90. So that's what I wrote right here. I also wrote that out in general here. The angles are technically complementary. So if I know this angle, cosine of the angle will be 90 minus that amount. And if I know cosine of this angle, sine will be 90 minus that amount. So in terms of problems with this, you could use a calculator for multiple choice, but I really want you to know this concept, so I also gave you a short answer problem. So for this one, it's multiple choice. So you could go through, plug in the x, see what the decimals are, or algebraically, we could say we know cosine and sine are equivalent, therefore the angles for the inputs must add to 90. I solve for that. It's multiple choice. I'd go back, double check. I would probably still use my calculator just to make sure those are the same. This one, no numbers. You really need to know the relationship, or you could draw it out like we did in that original example. If you have two angles that are complementary, so they add up to 90 degrees, which statement's always true? Oh, sine and cosine of the complements would be congruent. And then lastly, a little bit of short answer technically. What makes this hold true? So you don't have any options. You absolutely need to know that when you add the inputs of the angles, their sum needs to be 90 for sine and cosine to be equivalent. So I set up a little equation. I said x over 3 plus 30 plus x equals 90. I went through, I don't like that fraction, so I multiplied everything by the denominator of 3, distributed that. So goodbye to the 3's there. 3 times 30 is 90. 3 times x is 3x. 3 times 90, don't forget the other side, is 270. Did a little bit of manipulation. X ended up being 45. And notice, I checked. Why not? I went ahead, plugged in my x value. I got the same exact decimal.